Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. During the last episode, we discussed the thermodynamic definitions of temperature and pressure in terms of macroscopic variables, internal energy, entropy, and volume. We also explored the issue of entropy generation and the meaning of a reversible transformation. This led naturally to a prescription for mapping out the entropy of a substance by relating changes in entropy to heat flows into or out of that substance during a reversible transformation. The combined use of the first and second laws as a theoretical formalism for this purpose is sometimes called second law analysis. In lieu of a cartoon, today's meme is a clip from the 1991 film Terminator 2, in which a benevolent version of the T-800 android, played by Arnold Schwarzenegger, battles a T-1000, a more advanced android made from a fictional metal alloy that allows it to take various forms, including a traffic officer. In a climactic scene, the T-1000, played by Robert Patrick, gets doused in liquid nitrogen, setting the stage for Arnold's now famous words,
"Hasta la vista, baby."
Even if you've never seen this film, I'm sure you'll recognize the cinematic cliché of an impervious metal alloy becoming helplessly brittle after being sprayed with a cryogenic liquid. But is this really an accurate portrayal of what happens to solids upon getting cold? This turns out to be a great question for second law analysis. Let's first work out the details of how second law analysis works with gases and liquids. Then we can make our way back to the question of temperature and mechanical properties of solids. During the last episode, we discussed how second law analysis basically works. As a system evolves from one state to another, we consider the differential amounts of heat and work that must pass across the system boundary during the transformation, as well as the generation of entropy inside the system. If the transformation path is reversible, and thus the entropy generation inside the system is zero, differential changes in entropy can be tied to differential flows of heat divided by temperature. By integrating ds over the transformation path, we can determine the total change in entropy from state 0 to state 1. That's great in the abstract, but how do we do this in practice? To begin, let's return to the example of a gas in a closed piston cylinder assembly, which we considered previously in the context of mapping enthalpy as a function of temperature and pressure. Recall we picked a reference state, state 0, at low pressure and high volume, where the gas is ideal. As before, let's assume that the state we're interested in, state 1, is a non-ideal gas at higher pressure and temperature. As with enthalpy, entropy is a state property, and thus does not depend on which path we take from state 0 to state 1. This means that, just like enthalpy, we're free to construct a hypothetical path. Our principal requirement for each leg of this path is that it must be a reversible transformation. Also, just like internal energy or enthalpy, we usually want to choose our path such that it corresponds to previously measured properties, wherever possible. This latter consideration led us last time to the two-leg path shown here. In the first leg, we heat the gas at fixed pressure to an intermediate state at P equals P0 and T equals T1, state 3. Then in leg 2, we isothermally compress the gas at T equals T1 to the final pressure P1. Assuming we perform these transformations reversibly, we can determine the entropy change along the leg by examining the heat absorbed or released during these transformation steps. We can then determine the total difference in entropy from state 0 to state 1 by summing delta S for each leg. Recall that in leg 1, the gas is both ideal and of fixed pressure. Thus we can express dq for this leg as du plus p dv, corresponding to heat required to increase the temperature of the gas and do work against the piston face as the gas expands. Since pressure is fixed, this also corresponds to dH, which in turn can be written as Cp dt. Applying the second law, we can say that ds equals dq over t plus Sgen, where Sgen is greater than or equal to 0. Assuming this heat transfer is performed reversibly, meaning the temperature is the same everywhere within the system and at the boundary, we can say that Sgen is 0, and thus ds equals dq over t. Putting this together, the total entropy change along leg 1 will be the integral of Cp over T dt from T0 to T1. What this means is that if we've already measured the heat capacity of our gas, we don't need to do any further experiments to measure entropy. We already have all the information we need to calculate it. Now for leg 2. As with enthalpy, this leg is more complicated because the gas is not ideal along the entire path. The way this is normally treated is to integrate ds dp at constant t along this path based on the known PVT properties of the gas. Unfortunately, to do this properly requires a deeper mathematical discussion about how differential properties vary with each other in substances obeying the state postulate. This is the subject of Chapter 5 of our textbook, and something you'll cover in much more detail in Chemie 326. For now, though, let's just use the result, calculated for the Lee-Kessler equation of state. Just like the compressibility factor Z and enthalpy departure, H minus H ideal gas, the value of the entropy departure function, S minus S ideal gas divided by R, has been worked out already and is tabulated in our textbook. However, the use of this solution involves one additional complication we did not have with the enthalpy departure. In the case of enthalpy, which does not depend on pressure for an ideal gas, the ideal gas enthalpy of states 1 and 3, which share the same temperature, are the same. Thus, delta H for leg 2 corresponds directly to the enthalpy departure for state 1. However, the entropy departure is defined as the difference in entropy between a non-ideal fluid and the entropy of a hypothetical ideal gas at the same pressure and temperature. The entropy of a gas, even an ideal gas, does depend strongly on pressure. Thus, the entropy departure function only gives us part of delta S for this leg. The other part, the part for an ideal gas, we need to work out ourselves. We can look at that a couple of different ways. The first is to recall that for non-interacting molecules at fixed temperature, the entropy scales as R log of the volume. Thus, S1 minus S3 for an ideal gas is minus R log of P1 over P0. Another way to look at this is in terms of heat and work. For an ideal gas at constant temperature, U1 minus U3 is 0. Thus, heat and work are equal and opposite, with dW equaling minus PdV. Substituting the ideal gas law and then integrating, we come to the same conclusion. So thinking about this microscopically or macroscopically, we get the same answer. The ideal gas entropy scales as minus R log of the pressure. Thus, combining everything together, delta S for leg 2 will be minus R log P1 over P0 plus the entropy departure caused by non-ideal interactions among the molecules at pressure P1. For the Lee-Kessler equation of state, the entropy departure functions can be found in figures 5.7 and 5.8 and tables C5 and C6 of our textbook. Just like Z and the enthalpy departure, the total departure function is a sum of two terms, an S0 term and an S1 term for acentric molecules. Note that since this departure function comes from whatever equation of state we're using, we don't really need to make any additional measurements beyond the heat capacity and the PVT properties of the fluid. If we know these quantities, we already have everything we need to determine both enthalpy and entropy. Before proceeding with some practical examples, I'd like to again highlight a few limiting cases that tend to arise quite often, so deserve special attention. The first is the case of an ideal gas. Recalling the analysis we just did for delta S from state 0 to state 1, and setting the departure term to 0, we find that for an ideal gas, delta S is given by minus R log of the pressure ratio, plus the integral of Cp over T dt. Unlike enthalpy, entropy of an ideal gas is a function of both temperature and pressure, representing the dependency of multiplicity on both the energy content and volume of a group of molecules. As we'll see, this trade-off in contributions to the entropy places constraints on the spontaneous transformation path an ideal gas can take. Another important limiting case is incompressible liquids and solids. As I showed you previously, the internal energy of dense liquids and solids is largely independent of pressure because the molecules are already so close to each other, with an average volume determined by the temperature. A similar argument holds for entropy. If the molecules do not change their available volume significantly as a function of pressure, the multiplicity at a given temperature cannot change. So to very close approximation, the entropy of an incompressible liquid or solid is given by the integral of Cp over T dt, which for constant heat capacity is Cp log T. Finally, a third important limiting case is the change in entropy of a single component substance during a phase change, such as boiling of a liquid. As we discussed previously, the temperature and pressure are fixed during the transformation. Thus, if the transformation occurs in a closed system, Q equals delta H of vaporization. Assuming everything is done reversibly, ds equals dq over the boiling point, and thus delta S equals delta H of vaporization divided by the boiling point. So again, if we've already measured the enthalpy of vaporization and the boiling temperature, we can calculate the entropy of vaporization. We don't need to measure it separately. Okay, so now let's go through some examples. First, consider the problem of calculating entropy of a substance from known heat capacity and PVT data. In particular, let's revisit our previous analysis of the properties of normal hexane at 225 degrees C and 23.7 bar. Only this time, instead of enthalpy, let's focus on the entropy. Shown here is the hypothetical path we used. We chose 25 C and 1 atmosphere, where hexane is a liquid, as a reference state where enthalpy is defined to be 0. Let's also define entropy to be 0 at this point. From here, we heated the liquid at 1 atmosphere to the boiling point. We then boiled the hexane at fixed temperature and pressure, making a gas at T equals Tb. We then heated the gas to the final temperature of 225 degrees C. Finally, we increased the pressure of the gas to 23.7 bar. Using the expressions we just discussed, let's see if we can calculate the change in entropy along each of these legs in terms of data we have in our possession. The first leg is heating the liquid. As we discussed, the entropy of a liquid will be given by the integral of Cp over T dt. For the second leg, evaporation, we already know delta H of vaporization, so just need to divide by the boiling point to get delta S of vaporization. For the third leg, delta S is the integral of Cp over T dt. Since we're at low pressure along this path, we can use the ideal gas heat capacity correlation for hexane gas. Finally, for the fourth leg, we need to break our thinking into two parts. If hexane were an ideal gas, we could calculate delta S for this isothermal transformation as minus R log P1 over P0. However, we also need to correct this for non-ideal entropy departure at 23.7 bar and 225 C. Working through the details, for leg 1, we can use the same constant heat capacity we used previously for enthalpy. This leads to a logarithmic dependence of entropy on temperature. Plugging in numbers, we get about 27 joules per mole Kelvin. Leg 2 we get almost for free again. Dividing delta H of vaporization by the boiling point of 342 Kelvin, delta S of vaporization is about 84 joules per mole Kelvin. For leg 3, substituting the same three-term heat capacity correlation we use for enthalpy, we obtain an integrand with three terms. After integrating, we get a logarithmic term, a linear term, and a quadratic term. We already have the parameters we need from our previous enthalpy calculation. Plugging them in here, we get about 70 joules per mole Kelvin. Finally, for the fourth leg, since we used Lee-Kessler last time for the enthalpy departure with pretty good success, let's do the same here for entropy departure. We already calculated PR and TR, so we can just go to tables C5 and C6 and look up the values of the 0th and first order entropy departure functions, defined as the entropy departure divided by R. Assembling with the acentric factor and then plugging in the value of R, P1, and P0, we get a total entropy change of minus 37 joules per mole Kelvin. Note that delta S for this leg is negative. This reflects two things. The first is the decrease in molar volume, which reduces multiplicity. but the other is the negative potential energy associated with intermolecular forces. This lowering of potential energy at a given temperature means lower internal energy. As we discussed previously, at any given volume, internal energy is a monotonically increasing function of entropy. Thus, lower internal energy means lower entropy. After putting everything together for the four legs, we calculate a total entropy of 144 joules per mole Kelvin, which again is within about 2% of the value calculated from the NIST database. Not too shabby for a model based on heat capacity and a three-term PVT model. The second example I'd like to show you relates to the problem of converting heat into work. Recall that in episode A1 I showed you a small Stirling engine which uses the heating and cooling of a gas to convert some of the heat emanating from a cup of coffee to mechanical energy. As a first step in understanding this process, let's use second law analysis to consider the maximum amount of work we can extract from the adiabatic expansion of an ideal gas. More specifically, imagine we place an ideal gas in an insulated piston cylinder assembly and allow it to expand adiabatically and reversibly. What is the transformation path of the gas, and how much work can we extract? According to the first law, since there is no heat, du equals dw, and thus W is delta U. But we don't yet know the transformation path of the gas, so we can't just directly integrate dW as minus pdV. However, applying the second law and recognizing that the transformation is both adiabatic and reversible, ds must be 0 along the entire path. Thus delta S is 0. Invoking the entropy of an ideal gas, which we just derived, and setting delta S to 0, we find that T2 and P2 must be related. For simplicity, let's assume Cp is approximately constant, in which case we can solve in closed form for T2 versus P2. Reapplying the first law, we can thus calculate the work output based on delta U, resulting in the expression shown here. For example, assuming argon, which is a Cp of 5/2 R, and an initial temperature of 293 Kelvin, if we allow the gas to expand until the pressure drops in half, the temperature will drop to 222 Kelvin, and the total work output will be 885 joules per mole. This represents the maximum amount of work we can possibly extract from this transformation. One way to see this limitation clearly is to relax the assumption that the transformation is reversible and retain non-zero Sgen in our derivation of work. This results in an additional term that subtracts from the work output. According to the second law, Sgen can never be negative, so this term can never increase the work output beyond the case of Sgen equals 0, corresponding to a reversible process. This same basic principle can be applied to analyze the theoretical and actual efficiency of any process or process step. We'll come back to discuss this issue in more depth a bit later. Finally, the last example I'd like to show you relates to the physical properties of solid substances subject to mechanical deformation, in particular the elastic properties of rubber. When a rubber band is stretched, it resists this deformation, creating a force that seeks to restore the original shape of the rubber. To first approximation, this behavior obeys Hooke's law, which predicts a linear relationship between the imposed strain and the strength of the restoring force. Why does rubber behave this way? To explain this behavior, let's consider two possible analogies. The first is a coil spring. A coil spring consists of a metal helix, which when stretched, stores mechanical energy in the form of bond deformation among metal atoms. As long as the deformation is in the elastic range, meaning no atoms are forced to change their relative positions, this behavior obeys Hooke's law. In this case, all mechanical work done to the spring by stretching it is stored in the form of potential energy due to a slight increase in the overall average distance between metal atoms. In contrast, mountain bikes, cars, and other vehicles sometimes use something called an air spring. An air spring is basically a sealed piston cylinder assembly filled with air or some other gas that resists being compressed due to the increase in pressure of the gas with decreasing volume. If the gas remains isothermal, this type of spring also obeys Hooke's law. However, how is the mechanical energy stored when the air is compressed? Unlike the metal spring, the gas molecules are non-interacting, so they cannot store any potential energy. When the gas is compressed, the work of compression is exported as heat and stored in the environment as thermal energy. When the spring is released again, this thermal energy is converted back to work. In other words, an air spring is really a kind of heat engine that interconverts mechanical and thermal energy, not a device that stores and releases potential energy. Of these two analogies, which one is a better description of what's happening in a rubber band? Before committing to your answer, let's explore some key differences between the properties of metal and rubber. First, consider the metal. One clue is what happens to the position of the atoms when it's deformed elastically, as in a spring. Shown here is a 2D elastic solid cantilever composed of 76 Lennard-Jones atoms bound at one end. As the cantilever oscillates like a spring, we can see the atoms on the convex surface getting slightly further apart. This is reflected in the time oscillating potential energy, which reaches a maximum each time the cantilever reaches the maximum point of bending. Thus, although the atoms stay in the same relative positions, all the bonds stretch slightly, corresponding to a slight increase in volume. As we've seen, an increase in average distance between attractively interacting molecules, or atoms, causes an increase in potential energy. Another clue is what happens to the temperature of crystalline solids when deformed elastically like this. To first approximation, the temperature stays constant, suggesting that the work of stretching is converted into potential rather than kinetic energy. This being the case, what happens to the elasticity of metal when it's cooled to a really low temperature? Here we have a large plastic bucket full of liquid nitrogen, which at 1 atmosphere has a saturation temperature of 77 Kelvin. That's minus 196 degrees C. So pretty cold. Cold enough to shatter the Terminator, apparently. But what does it do to our coil spring? As you can see, it pretty much does nothing. The metal is just as springy and elastic at 77 Kelvin as it was at room temperature. But I think this actually makes sense given our understanding about how the metal accommodates an input of mechanical energy. The spring metal is crystalline, so it's already frozen. There's nothing about being cold that interferes with the ability of the bonds to stretch in response to a stress. Of course, if we try to bend the metal beyond its elastic limit, we might find it's less able to deform plastically at 77 Kelvin, making it more brittle. But we'd still have to overcome its yield stress, which for most steels is quite high. So the idea that all metals become fragile like glass when cold does not seem to align very well with reality. So where is this cinematic cliché actually coming from? To answer this, let's now think about our rubber band. How does a rubber band accommodate the mechanical energy of being stretched? One clue is that rubber, unlike metal, has a Poisson ratio of 0.5, which means it does not change volume upon being stretched. It gets longer in one direction, but shrinks along the other two axes. Since potential energy is tied to the average distance between molecules, it's hard to understand how the potential energy could change if the volume cannot. Also, the rubber heats up slightly when stretched, and cools again when unstretched. You can feel this yourself if you place a rubber band between your lips and rapidly stretch or unstretch it. I've added a link in the playlist to a video demonstrating this effect with an infrared camera. So what happens to the elasticity of rubber when cooled to very low temperatures? Let's repeat our previous experiment, but this time with our rubber band. In this case, it appears that all the elasticity our rubber band had at room temperature is completely gone. What we're left with feels like a stiff piece of plastic. I can pull on it, but no longer absorbs any mechanical energy. To take this one step further, let's see what happens to a flexible rubber toy if we soak it in liquid nitrogen until it reaches equilibrium at 77 Kelvin. As you can see, it also has lost all elasticity, and in addition is quite brittle. This is starting to look a lot more like what we saw with the T1000. So how do we explain these differences in properties of rubber versus metal? One thing to look at is the molecular structure of rubber, which unlike metal is not a crystalline solid with atoms in a regular arrangement. Rubber is a polymer composed of isoprene monomers that are chemically bonded to each other in long chains, hundreds or thousands of monomers long. These chains form a spaghetti-like structure, where the individual monomers are free to move, as in a liquid. However, the individual chains are also cross-linked at various points, which anchors the molecules and keeps them from drifting long distances. As a result, the chains flail around randomly between cross-link points. What this means is that when we stretch the rubber, we're not really able to stretch bonds in the same way that we can in a crystalline metal. All we can really do is alter the constraints on how the molecules move around. This brings us to the central issue of what happens when we stretch rubber. Imagine two cross-link points separated by some distance. When the rubber is stretched, these cross-link points will, on average, become further apart. The polymer is space-filling, so the molecules around this segment adjust to the new arrangement, much like a liquid does. So we don't expect a change in potential energy. However, the number of ways the segment can rearrange itself randomly as it flails around will be slightly lower. To better see this, here is an MD simulation of a 40-segment chain of 2D Lennard-Jones molecules that have been permanently bonded together by Gaussian springs. Both simulations shown here have the same chain length, total energy, and temperature. But they differ in the distance between the crosslink points, connecting them together. If the crosslink points are close together, the flailing of the polymer chain does not pull the crosslink points in any particular direction on average. But as the crosslink points get pulled further and further apart, the random motion of the chain begins to exert an average force that pulls the anchor points toward each other. The thermodynamic explanation for this effect is that the multiplicity of each segment decreases when it is stretched out because it has fewer ways to rearrange itself. You can actually see this in the video shown here. Just watch for a while, paying attention to how far away the flailing chains get from the anchor points. You'll notice that the chain in the stretch state is a bit more restricted in the ways it can rearrange, corresponding to this reduced multiplicity. Thus, even though the internal energy does not change as the anchor points move toward each other, the multiplicity increases, and so this is favored by the second law. This is exactly analogous to an ideal gas exerting pressure on the walls of a container. Even though the internal energy of the gas does not change as the volume expands, the multiplicity does, so expansion is favored. If we lower the temperature sufficiently, individual monomers and chains will bind together into an amorphous solid structure, like a glass. Since the polymer chains can no longer randomly reconfigure themselves, and thus explore new configurations, the entropic basis for elasticity is lost, and the material just becomes a rigid, solid material. As in a glass, the bonds between molecules in latex are not very strong, so if deprived of its elasticity, it is easily fractured. The entropy of randomly flailing polymer chains was modeled in the 1940s by Leslie Treloar and others, using something called the affine network model. The result, shown here, is that the entropy of a uniaxially strained piece of rubber decreases with strain. Here, alpha is the strain ratio, defined as the length of the rubber band divided by its length with zero strain, L0. R is the ideal gas constant, and m is the average molecular weight of the polymer segments between crosslinks. Meanwhile, if we assume the polymer has a constant mass-specific heat capacity and no potential energy from stretching, the internal energy will depend linearly on temperature. This implies the entropy at fixed strain will scale as Cp log T, as we saw earlier for other incompressible liquids or solids. Putting these entropy contributions together, we get the dependence shown here, where S0 is the value of entropy in the unstretched state at a reference temperature of T0. If you haven't fully caught on to the analogy yet, here is a comparison of the internal energy and entropy of the stretched rubber band compared to the internal energy and entropy of an ideal gas of constant heat capacity. Unlike a metal spring, Neither of these systems can store any potential energy. But both these systems do something that the metal does not. They undergo a reduction in entropy upon being deformed, which can drive heat flow and thus act to convert work to thermal energy. To see this played out, imagine a rubber band that has been previously stretched to twice its unstrained length and allowed to come to equilibrium with the ambient temperature. Imagine we quickly, meaning adiabatically, but reversibly, allow the rubber band to contract to its normal length. What happens to the temperature? Since the transformation is adiabatic, we know heat is zero. If it's reversible, it means Sgen is also zero. Writing out the second law, these constraints imply delta S will be zero, just like the adiabatic expansion of an ideal gas we examined earlier. Our initial entropy, S1, is known, since we know the initial temperature and strain state. Plugging in alpha equals 2, we get a negative initial entropy, reflecting the reduced multiplicity of the polymer molecules in its stretched state. Since delta S is zero, this implies that the higher entropy of the polymer when unstretched must be balanced by a reduction in temperature. Introducing T2 as an unknown and then setting S2 equal to S1, we can solve for T2. The resulting expression shows the temperature will decrease by an amount related to the heat capacity and the chain length between crosslinks. For a typical estimate of M for latex rubber, this drop in temperature is about a ½ degree C or so. This is a large enough drop it can be detected by an IR camera, as shown in this YouTube video by Ben Krasnow. A link to the full video is in the playlist. Note that if the rubber band is stretched and then immediately unstretched, it briefly increases in temperature, but does not have time to transfer any heat to the environment, so returns to the original temperature when returned to its original stretch state. But if we wait a few seconds after stretching, the rubber band reestablishes thermal equilibrium with the environment. Thus, when it is finally unstretched, it gets colder, just as we calculated. That's as far as I wanted to take this example here, but you'll find more about this on the problem set, where I ask you to take a closer look and try to solve for the spring constant of a rubber band based on considerations of the work required to stretch it. As you've probably noticed, the same basic issues keep coming up over and over again in these examples. As we'll see, the way energy content and entropy change in response to changes in the state of the system is a common underlying issue governing reversibility and equilibrium in any system of molecules.